Hello and welcome to this new example. In this example, we will reconsider the engine in the previous example. So remember, in the previous example, we had a 3-liter 6-cylinder engine. So the displacement volume was equal to 3 liters and the total number of cylinders is equal to 6. Now this engine is connected to a dynamometer which gives a brake output torque reading of 205 newtons meter at 3600 rpm. So the torque for this engine is 205 newtons meter measured at an engine speed of 3600 rpm, which is divided by 60 will be equal to 60 rps. Now at this speed, air will enter the cylinders at 85 kilopascal and a temperature of 60 degrees Celsius. So the intake pressure is equal to 85 kilopascal and the intake temperature will be equal to 60 degrees Celsius, which is of course equivalent to 333 Kelvin. Now the mechanical efficiency for the engine is 0.85 or 85%. So remember that the mechanical efficiency will account for all the power lost by the engine. So the power loss, as we said, is due to mechanical friction losses, due to pumping losses, and due to accessory power needs. Now, in part A, we need to calculate the brake power, so W dot B. Now, since we know the torque and the engine speed, we can calculate the brake power at the engine speed of 60 rps, which is equal to 2 pi tau n. So 2 pi times the torque 205 times the engine speed of 60 rps, which is equivalent to 77.3 kilowatt. Now part B, the indicated power, W dot I. So of course here the indicated power will be greater than the brake power, as we said, due to losses. So the indicated power is the power transferred from the gas to the piston, and the brake power is the power transferred to the crankshaft. So eta mechanical will relate the indicated power to the brake power. So it is equal to the brake power divided by the indicated power. So as a result, the indicated power will be the brake power divided by the mechanical efficiency. So 77.3 divided by 0.85, and it is equal to 90.94 kilowatt. Now part C, the brake mean effective pressure, the Bmep. So the Bmep for a 4-stroke engine is 2W dot B divided by VDN. So 2 times 77.3. So here I will leave the brake power in kilowatt, and as a result we will obtain a brake mean effective pressure in kilopascal divided by the displacement volume, which is 3 liters. So 3 times 10 to power minus 3 to convert to meter cube, times the engine speed. So the Bmep in this case will be equal to 858.89 kilopascal. Now the indicated mean effective pressure, the IMEP, we can find the IMEP also by using the mechanical efficiency. So we said that eta mechanical is the brake power divided by the indicated power. So the brake power is proportional to the brake mean effective pressure, and also the indicated power is proportional to the indicated mean effective pressure. So we can say that this equation also to the Bmep divided by the IMEP. So we can calculate the IMEP from knowing the mechanical efficiency and the Bmep. So the IMEP will be the Bmep divided by the mechanical efficiency. So 858.89 divided by 0.85, which will be equal to 1010.46 kilopascal. Now, in part E, we need to calculate the friction mean effective pressure E, the FMEP. So as we said, the friction mean effective pressure is the difference between the IMEP and the Bmep. So the friction mean effective pressure will account for the mechanical friction losses, for the pumping losses, and for the accessory power needs. So this will be 1010.46 minus 858.89. So the friction mean effective pressure will be equal to 151.57 kilopascal. Now, in part F, W dot F, the power lost to friction, W dot F. So the power lost due to friction would be the difference between the indicated power and the brake power. So the indicated power is 90.94 minus the brake power, which is 77.3, which will be equal to 13.64 kilowatt. Now part G, the brake work per unit mass of gas entering the displacement volume of one cylinder. So we need to calculate the brake work, W dot B, divided by the mass entering the displacement volume of one cylinder. Now the mass entering the displacement volume of one cylinder will be equal to the density of the gas entering the cylinder times the displacement volume for one cylinder. So to calculate the density, since we know the pressure, which is 85 kilopascal, and the temperature, which is equal to 333 Kelvin, we can use the ideal gas law. So the ideal gas law states that the pressure is equal to the density multiplied by the gas constant multiplied by the temperature in the intake manifold. So we will consider the gas as air here. So the gas constant for air is 287 joule per kilogram Kelvin. So the density will be equal to the pressure divided by RTI. So the pressure is 85 times 10 to power 3 to convert to Pascal, since we have here the R in joule per kilogram Kelvin. So if we put the gas constant as 0.287 kilojoule per kilogram Kelvin, of course the pressure will be 85 kilopascal. Now R here is 287 times 333. So the density will be equal to 0.89 kilograms per meter cube. So the mass of the gas entering one cylinder and covering the displacement volume will be equal to 0.89 multiplied by the displacement volume for one cylinder, which is the displacement volume for all the cylinders, 3 liters, divided by the total number of cylinders, which is 6, times 10 to power minus 3 to convert it from liters to meter cube. So the mass in this case would be equal to 0.445 grams. So this is the mass of the inducted gas into one cylinder, and that will cover, of course, a displacement volume of half liters. Now we need to calculate the brake work, WB. And previously we have obtained a relationship between the brake power and the brake work. So we said that the brake power, W dot B, will be equal to the total number of cylinders multiplied by the engine speed divided by 2 multiplied by the brake work. So this is the brake work for one cylinder and during one cycle. So the brake work in this case will be 2W dot B divided by NCN. So 2 times 77.3 divided by the total number of cylinders multiplied by 60, and it will be equal to 0.43 kilojoule. And of course here you can calculate the brake work in another way. So from the definition of the brake mean effective pressure, this is the work per displacement volume. So the work for one cylinder and during one cycle per the displacement volume of one cylinder. So we can say that the brake work in this case is the brake mean effective pressure multiplied by the displacement volume of one cylinder. So the brake mean effective pressure calculated earlier is 858.89. So 858.89 multiplied by the displacement volume of one cylinder, which is 3 divided by 6 multiplied by 10 to power minus 3. So also you'll obtain the brake work equal to 0.43 kilojoule. Now the brake work per unit mass of inducted gas per MI will be equal to 0.43 divided by 0.445 grams. So it will be equal to 0.965 kilojoule per gram of inducted gas. And also you can calculate it in kilojoule per kilogram by multiplying this number by 1000. So we'll obtain 965 kilojoule per kilogram of inducted gas.